Hello. So, in this topic, we'll learn how to make the relationship between the inside pressure and outside pressure across the spherical surface. And obviously, we'll be dealing with only single surface. If there will be multiple surfaces, we'll cross them one by one. So, whatever formula we are going to make, that formula will be valid for single surface. Multiple surface, we have to do the modifications. Okay. So, if you remember, in the beginning, when we defined the pressure, at that time, we calculated the pressure across the plane surface. And at that time, we learned that if it is a plane surface, the pressure on either side was same, but only for plane surface. In this case, we will learn that pressure on either side of the spherical surface is not same. It is related with tension, surface tension and the radius. Okay. So, we have taken this spherical surface, single spherical surface is there. Inside pressure we have taken as P in and the outside pressure we have taken as P out. This spherical surface has a radius R and surface tension here is T. So, we want to make relationship between the P in, P out and the tension. Okay. This spherical surface experiencing the three forces, one from the inside, one from the outside and one across the surface, that is coming because of surface force, these three forces. The thing is, if I start calculating these three forces for the whole spherical surface, these three forces individually will be 0. If we calculate the net force because of P in onto this whole spherical surface, that will be 0. Individually due to P out will also be 0, and individually due to the surface tension, it will also be 0. So, I have to do something, and that something is I'll cut this whole sphere into half. If I cut this in half, the force due to P in will become non-zero. Force due to P out will also become non-zero and the surface force will also be non-zero individually, but combined will remain 0. Okay. So, that's what we will do. We'll cut it in half and we'll calculate these three forces separately and the net force we will make it 0. Okay. So, this is my half sphere. I've cut this sphere in half. This is my half sphere, and in this sphere if you see, this is the periphery of the sphere. And since this is the periphery, so first I'll calculate the surface force. This surface force will be acting everywhere onto the surface and everywhere it will be 0 except at the periphery that we learn. At the periphery, this surface force will be non-zero. So, if you remember regarding the surface force, this surface force always acts within the plane. Within the plane, it always tries to minimize the cross-section area and it always acts perpendicular to the periphery. So, if you go perpendicular to periphery and within the plane, you'll have only this kind of force. And this force is applied by the other half. By this lower half is applying this surface force. Okay. So, we will calculate this force. So, if you see the periphery, the total length of the periphery will be 2 pi into r. So, Fs upon 2 pi r will be equals to capital T. This length of the periphery will be 2 pi r because r is the radius and we have cut this in half. Okay. So, that will lead to Fs to be 2 pi r into T. That's my equation 1. So, the surface force applied by the other half onto the first half is equals to that much. Okay. Now, we will calculate the force applied by P in. So, if you remember, we have a formula, F perpendicular upon cross section area is P. That's the formula. So, the pressure, the force which is responsible for pressure, that force always acts perpendicular to the cross section area. And if we go perpendicular to the cross section area, will always pass through the center. So, this P in will apply the force in this direction, perpendicular and outside, and this P out will apply the force towards the center inside. This is due to the, I'm calling this F in stands for P in and I'm calling this F out. This is stands for P out. The thing is, both of these forces, the magnitude wise they will be different, but the behavior of both of these forces will be same. If I calculate the net of F in and net of F out, the only thing which will be different will be the direction and magnitude. The formula will have some sort of a resemblance between these two. So, what we will do, we'll only calculate one force and that is this one. And then from there, we'll try to modify, we'll try to get the other force just from the formula for F in. Okay. So, now we'll try to calculate the force applied by P in. So, if you see here in this diagram, this force will be acting perpendicular and it will supposed to pass through the center. This is the force, and it will be changing its direction. At different point, it will be in the different direction, but it will always be towards the radial direction. Okay. So, to calculate it, we'll make one more half circle. Let's make it. So, this is the half circle we are making, and we want to calculate the Fn. So, to calculate that, what we will do, we'll have to do the integration there. So, I am going for angle theta. I am measuring the theta from this line. This is angle theta. I went for theta, and after going for theta, I make a line which is cutting the sphere. And similarly, one more line we have drawn at an angle theta plus d theta. So, this is d theta. So, this line, we cut the, we went for theta, we make a line, and then we make a circle. So, we made a line and we rotate that line. Similarly, we made the second line, we will also rotate that line, and if we rotate the second line, it will be like that. So, we made two lines. We went for theta, we made a circle, then we went for theta plus d theta, we again made a circle. So, when we made this circle, we'll get this strip of circle. This is the strip we will get. And you see, every point onto this strip is symmetric with respect to every other point with respect to this line. Okay. So, when we calculate the Fn, the force due to the pressure will be acting perpendicular in this direction. Okay. I am calling this dF because you see, this force is acting onto the element, small element of this hemisphere. Okay. So, let's take two components of this. I take two components, one along this line and one along the radius. So, if I take two components, this angle is theta, this angle is theta. If this angle is theta, this angle will also be theta. So, this will be dF cos theta and this will become dF sin theta. Okay. So, now you can see this dF sin theta is acting in this direction and dF cos theta is acting in this direction. And since we have to go for whole circle, if we keep going on to the whole circle, this dF sin theta will keep rotating like that. And everywhere it will be dF sin theta. And you see, when we go for a whole circle, this dF sin theta corresponding to every dF sin theta, you will find an equal and opposite dF sin theta onto the other side. Here, you will find. So, each and every dF sin theta will cancel out each other. So, when we will actually calculate the component of this force due to the P in onto this element, that component will only have this one. Because each and every dF sin theta will cancel out and each and every dF cos theta will add. Okay. So, if I calculate dF in acting onto the element, that will be equals to dF cos theta. Okay. Now, let's calculate the value of dF. So, we have this formula. This dF is coming because of P in. See, we have this formula and in this formula, there is this area. We have to calculate the area of this strip. Now, this is my equation 1, 2 and this is my equation 3. So, now we have to calculate the area of this strip. Now, this strip, the radius of this strip is, this is R, this is theta, this is R and this is theta. So, in this triangle if you see, this will become R sin theta. R sin theta. So, this radius of this strip will be R sin theta. Now, we have to calculate the width also. So, width of the strip, this is the width. Width of the strip will become R d theta. This is our radius and this angle theta. So, we are making the angle, we are making a slope. So, R d theta. So, this is a circle. So, to calculate the area of this circle, what we do, we cut the circle and we open it. So, when we cut the circle and when we open it, it will look like it's a rectangle. And we know how to calculate the area of the rectangle. That is total length multiplied with width. This R d theta is the width and the total length will be equals to the length of the periphery. So, dA will be 2 pi R sine theta, which is the length of the periphery, multiplied with r d theta, which is width of this circle. So this dA will become 2 pi r square sine theta d theta. That is my equation 4. Okay. So let's put that in this equation. So dF in divided by dF divided by cross section area 2 pi r square sine theta d theta, and that will be equals to P in. So when we will calculate the force due to the P out, in place of P in, we'll just write the P out, and direction of force will be inward in that case. So this dF becomes 2 pi r square sine theta multiplied with P in d theta. Okay, we got the dF. Now we have to put this value in this equation, equation 3. This is my equation 5. So from equation 3, if you put the value, this dF in will become 2 pi r square into P in sine theta, and cos theta will come from there, cos theta d theta. Okay, so this is the dF in this term. So all we have to do, we have to integrate that thing. So when we integrate with respect to theta, 2 pi r square will not be changing, P in will not be changing. And this thing, you see, sine theta and cos theta, what we can do, we can take 2 from here, so 2 multiplied with sine theta, cos theta will give you sine 2 theta. So this whole value will become pi r square into P in sine 2 theta d theta. This will be dF in. To calculate F in, we do have to integrate dF in, and the limits, obviously you see, limits will be from 0 to pi by 2, not from 0 minus pi by 2 to pi by 2, because you see, when you move theta with respect to this line, so when you will be going till pi by 2, you are taking the circle. So when you go from 0 to pi by 2, all the circles will be taken, and all those circles will create a hemisphere. So limit will be from 0 to pi by 2. So we'll put the value, that is pi r square into P in integration of sine 2 theta d theta from 0 to pi by 2. So we have to integrate sine 2 theta d theta. The formula we know. We know the formula how to integrate that. So pi r square into P in integration of sine 2 theta is 1 by 2 cos 2 theta negative. Limits from 0 to pi by 2. So that value will be pi r square into P in by 2, and let's put the value. So when you put the pi by 2, it becomes cos 2 into pi by 2, that becomes cos of pi. So minus of cos pi, minus minus will become positive, and you put 0, that is cos 0. So that becomes pi r square into P in by 2. Cos pi is minus 1, and minus minus will be plus 1 plus 1. So that value will be pi r square into P in. So that is equals to F in. This is the force applied by the P in onto the hemisphere, and this direction of this force is outward. And as we discussed in the beginning, the force due to the P in and the force due to the P out, that will be opposite in direction. The behavior of both the forces will be same, and in this formula you can see the R is a constant. This capital R does not depend upon the P in. The direction is outward. This direction is outward. Outward along this line, meaning along the perpendicular bisector. So if I want to calculate the F out, from the same formula I can write it as pi r square into P out, and the direction of this force will be inward. You see. So now we have the force due to the P in as well as the force due to the P out. Both of these forces I am having along with the force due to the surface tension also. I am having this force also. Now to make the relationship, all I need to do, I need to make the FBD. And after making the FBD, I'll get the relationship between the P out, P in along with this Fs, which is the surface tension, which is in terms of surface tension. Okay, so now we have to make the FBD. So we'll make the FBD. If we make the FBD, we have to show the forces. So there is this force which is acting outward, which is F in. There is this force which is acting inward, which is F out. And there is this force which is acting again inward, which is Fs. Okay, these three forces are there and the system is not at all moving. It's not moving at all. So if we balance these forces, I'm doing it here. If we balance these forces, the F in should be equals to F out plus Fs. We have the F in, we have the F out, as well as we have the Fs. We'll put all the values there. So the F in will be equals to pi r square into P in. F out is equals to pi r square into P out, and the Fs is equals to 2 pi r T. Okay. So if we rearrange this equation, or we can divide this whole equation by pi r square, if we do that, we'll get the relationship which is equals to P in is equals to P out plus 2T by R. That's the relationship we are getting between the inside pressure, outside pressure and the surface tension. This is the relationship, and from this relationship you can see the inside pressure and the outside pressure, it's not same. They are different. But in this relationship, if you put the value of R to be infinity, this whole term, and infinity is for the plane surface, the radius is infinity for plane surface. If you put it infinity, P in and P out will become same. So you can see the relationship. Earlier we used to say the pressure across both the side of a plane surface is same, and that's the same relationship we are getting from here also. So this is the formula between the inside pressure and outside pressure across the spherical surface. One more thing, this formula is only valid for single surface. So whenever you cross a surface, spherical surface, whenever you cross a spherical surface, there is always a pressure change happening, and that pressure change is equivalent to 2T by R. So the inside pressure is more. So whenever you from the outside, you try to come inside, there will always be a pressure rise equivalent to 2T by R. And when you go from inside to outside, there will be a pressure drop that is equivalent to 2T by R. And the thing is, if there are two surfaces, so you have to cross them twice. If there are two surfaces, one time when you will cross, the pressure difference will be 2T by R, and the next time when you will cross, the pressure difference will be another 2T by R, and that will make it 4T by R. So for the single surface, this is the formula, and if there are double surfaces having the same radius, so for double surface, if there is a double surface, multiple surface, double surface, then the relationship will be P in is equals to P out plus 4T by R. But in this case, the radiuses has to be same. If the radiuses are not same, then it will be 2T by R1 plus 2T by R2. Okay. So one more time, we'll summarize this thing. We wanted to make the pressure relationship across the spherical surface. So when we have a sphere, there will be three types of forces which will be acting onto it. One, due to this inside pressure, and this force will be outward direction and it will be passing through the center. It will be perpendicular to the surface area. Second, due to this outside pressure, it will also apply the force onto the sphere. This force will be perpendicular to surface. It will pass through the center. And there will be one more force which will be acting only at the surface and which will be due to the surface tension. That is surface force. So we cannot proceed with whole sphere because otherwise individually all three forces will be zero. So what we do, we cut the sphere, and after cutting the sphere, we studied these three forces separately onto the hemisphere. So first we calculated the surface force here. We had the formula, and that surface force will be only acting at the periphery, which is circular in nature. So length is 2 pi r. So Fs upon length of the periphery is equals to T. From there we get surface force, which was equals to 2 pi r multiplied with T. Okay. Then we proceed towards the pressure force. There is a general formula between the force at the surface and the pressure. F perpendicular upon A is equals to P. So to calculate the pressure force, we started with inside, F in only. Okay. So what we did, since the force will be changing its direction, everywhere it will be having a different direction, so we cannot just apply this formula because area keeps changing. So we went for theta, from the perpendicular we went for theta, we made a sphere, circle, then we further went for theta plus d theta, we made one more circle. So between these two circles, we had this circular cross section area, this small circular cross section area. At a small point here onto the cross section area, we have defined the force due to the pressure is dF. This is not the net force onto the whole sphere, meaning we are taking only at this point. And since this force will be perpendicular to this cross section area, we took two components, one in this direction, second in this direction. One is dF sin theta, other is dF cos theta. Okay. But we have to calculate force onto this whole element. So when we do, ultimately this is a small element onto this whole element. So what we did, we moved across this whole element. So when we will be moving across this whole element, all these components, dF sin theta components, will be cancelling out each other. So this time we are calculating the pressure force onto this whole element, circular element. So all these dF sin theta will cancel out each other, and all these dF cos theta will add. So net force due to the inside pressure will be equals to dF cos theta. This dF is this force. Then we went to calculate this dF. To calculate this dF, I need this formula. So I need to calculate the cross section area of this. To calculate the cross section area, I calculated the radius, which was r sin theta. I calculated the width, which is r d theta, and I took it out, this circle, I cut this circle, I make it flat. So in that case, it is approximately resembling a rectangle, which has length equivalent to 2 pi r sin theta, because r sin theta is the radius, and the width equivalent to r d theta. That gave me my area. That is the area. Then from this formula, dF upon area is equals to P. I applied that formula and I got dF. By putting the value of dF in this formula, I got the force acting onto this element, net pressure force acting onto this element due to the P in. And that net force was this one. I simplified this and I integrated it, I calculated this force. So result was this. F in, we calculated pi r square into P in. That much was the force acting because of the inside pressure. Based upon this formula, we got the idea to calculate the F out also, which was equals to pi r square, and only thing we did, we replaced the P in by P out, because only thing different in this case will be the direction of force, and the magnitude from here you get. So we get, individually we get F in, individually we get F out along with the Fs. Then we made the FBD for this hemisphere. We place the forces F in, F out as well as Fs. Acceleration has to be 0 because this hemisphere is not moving anywhere. So here we made the equation. Here we made the equation. We simplified the equation, and this is the final result we got. That result is P in is equals to P out plus 2T by R. All these relationships, all these formulas, all these calculations we did for single surface. So this formula is valid for single surface. So based upon that, we deducted that whenever we are going to cross a spherical surface, there will be a pressure change equivalent to 2T by R, which will be happening. If there are multiple surfaces, what we will do? Every time we will have a pressure difference, we'll add it. So if I'm having a double surface, and the surface, double surface means like this, meaning we'll have some width. So there is one surface, there is two surfaces, and both of these surfaces are having same radiuses. That's a condition. If they are having same radiuses, so when you cross this surface, there will be a pressure difference of 2T by R which will come, and when you will cross this surface, there will be a further pressure difference of 2T by R will come. That will make it 4T by R. Okay. So that's how we derived the formula. That's how we made the relationship between the inside pressure as well as the outside pressure. Okay.